Okay. Can a photon from an X-ray ionize a magnesium atom to magnesium 2+? Can it do that? And happy to walk through this one together here. It's not as simple. Okay, so crew, let's first figure out the energy it's going to take to ionize this magnesium atom. There's two different ionization energies in this process. Doing this to this requires us to sum the first ionization energy and the second ionization energy equals total energy. So if we look at the numbers for that process, the first ionization energy is 736. The second ionization energy is 1445. So 736 plus 1445 equals 9712 kilojoules per mole. Double check my math, please, but I think that's right. So doing this process requires 2179 kilojoules per mole. Yeah.
Would you give us this chart?
Oh yeah, of course.
Where do you get that required?
So I summed. Yep. No, but a good question. This is the energy to remove one electron. This is the energy to remove the second electron.
Okay.
And I want to get rid of both of them. Because the 5, yeah. Oh, yeah. 81. Good catch. Yeah. But let's actually do this first. Crew, my question, I'm actually not concerned about ionizing a mole. I'm concerned about ionizing a single atom. So let's divide this value by Avogadro's number, because this is the energy per mole. I care about the energy per one atom. So let's take 2181, thank you for the catch on the math, kilojoules per mole, and multiply it by, 1 mole per 6.022 times 10 to the 23rd atoms. And crew, this would give us the kilojoules per atom. And maybe we want to do one more thing. Maybe we want to convert this to joules too. So maybe we also want to say there's 1,000 joules per kilojoule. So if we look at what we cancel kilojoules, we cancel moles, we'll be left with joules per atom. The number of joules required to ionize a single magnesium atom. I messed up on my addition. I'm definitely going to need some help here on the division and multiplication. So I guess I'll go a little bit louder, please. Joules per atom. And I think worth repeating, that's again to do this, to strip those 2 electrons off. Yeah.
Like something like this on the assessment, would you let us know what units we're looking for?
The reason I knew to convert to joules is ultimately when we take the wavelength of our wave and we convert it to a frequency and then to an energy, that's going to come out in joules. So I just sort of anticipated that. I probably wouldn't, because all you're looking to do is compare 2 values.
Okay.
You're looking to compare the energy in the X-ray to the energy required for this process. So I would just expect you to get it in the same units. You could put them both in kilojoules or both in joules. It doesn't really matter. But I sort of foresaw that we were going to have a mismatch in units there and went ahead and converted this one. So we've got an energy per atom, but now we've got to figure out how much energy that a photon of an X-ray carries. So let's copy that number down. We have an X-ray that has a wavelength of 2.5 nanometers. Let's get this on the screen there. So our X-ray is 2.5 nanometers, which is the wavelength. So crew, we could do this in 2 steps. We could say the frequency equals the speed of light divided by the wavelength. And then we could say the energy of a photon equals Planck's constant times the frequency. Or we could sort of sum those things together, and we could say the energy of a photon equals Planck's constant times the speed of light over the wavelength. I think we should probably do the latter option. We should probably do that. So we'll bring this down here and we'll say the energy of a photon. You get the constants on the assessment. Anyone off the top of their head remember Planck's constant? Getchell says something. That something is 6.63 times 10 to the minus 34 joules times seconds. Yes, yes. Yep. 34. And again, you get it on the assessment, Joe. Yeah, yes, we'll convert that too. Yep. Speed of light. Again, you get the speed of light in the assessment. We'd have 10 to the 8th meters per second. Our wavelength was 2.5 nanometers. Now, what you won't get on the assessment is the conversion of nanometers to meters. How many nanometers do we have in a meter? That's micro. Nano is a billionth, a ninth, 10 times to the ninth. So we'll say 1 meter is 1 times 10 to the ninth nanometers. So what that gives us is 2.5 times 10 to the minus 9 meters. People that are live, can you see this okay? I know it's getting a little bit small for people in the back. June, looks like you can see it okay on the screen here. So the energy of a photon, let's just look at our units, make sure we did our units right. Seconds will cancel, meters will cancel, leaving us with joules. That sounds like a really good energy unit. I'm definitely gonna need some help here, team. We've got 6.63 times 10 to the minus 34 times 3 times 10 to the 8th divided by 2.5 times 10 to the minus 9. Let me get a couple of votes on this one. There's enough parentheses and exponents there that I think we'll want to check our work. $7.96. We got minus, oh, we'll have to do 34 minus 8. So, what's up?
What was the units that the speed of light was?
Meters per second. Meters per second. Yeah, 34 minus 8 is 26. So that'd be minus 26 minus 9 minus 9, 17. Yeah, come on, team. I asked you for help here.
What's the exponent of speed of light? 8?
10 to the 8th. 10 to the 8th.
So you add that and then you like add.
So yeah, I did minus 34 plus 8 gets minus 26
Over -9.
minus 9, which is like plus 26. So, or plus 9, excuse me. So minus 26 plus 9 would be minus 17. So crew, each yeah. Meters per second. This is what you asked for? Yeah, speed of light, meters per second. So crew, each photon of an X-ray carries that much energy. That's the energy it requires to ionize a magnesium atom. So you hit a magnesium atom with a single photon. Does it ionize? I think it does. Because remember, we're negative exponents. This is a bigger number than that is. They're both really, really small numbers. So we're talking tiny atoms. This is a bigger number than that is.